OK, but we need to start simple. OK, so we're going to start with a little reminder about Cartesian geometry. So if I give you a plane and ask you to tell me where I am in the plane, you can do that with two numbers, so-called x and y coordinates from Cartesian geometry. Or if you've done a little bit of the planar polar coordinate system, you can tell me where I am by telling me some angle I make with some axis and how far I am from some origin, so-called r and theta. And there's a little relationship between Cartesian coordinates and polar coordinates, which says the x coordinate is just the radial coordinate r times the cosine of this angle, and y is r sine theta. So lift your hand a little bit or nod your head if you've seen these sorts of formulas before. OK? Most of you. And this is all we're going to need today, really, to plot these shapes. OK? So you can go away armed with the knowledge you already have and start to generate the shapes that I've already shown you. OK, anybody here heard of Pythagoras? Yeah. OK, so if I ask you how long this thing is here in terms of x and y, what is it? Fantastic. It's x squared plus y squared. The distance along here is x squared plus y squared. All square rooted, somebody mumbled at me. Thank you very much. Now I want to generate these twisty shapes, OK? And as I said, we'll start easy. We'll start in the plane, OK? Now I want to generate helices. So I want to, now here's a cartoon. It's a spiral. How do I write the equation of this spiral? Well, in polar coordinates, it's very, very easy. I just say theta, the angle in polar coordinates, is some function of the radial variable r. OK? I mean, in Cartesian, this would be y is some function of x, but it's much more natural to use these sorts of forms to specify spirals. And this one here, theta, is some constant times r, is a very, very famous one that's called the Archimedean spiral. OK? Just imagine we're here, OK? And I'll start rotating around. OK? So the angle is increasing. From this formula, you can read off that r is theta upon a. So as the angle increases, the distance from the origin increases linearly with that angle. Okay? And that's why you get these regularly spaced spiral arms. Okay? But there are more complicated spirals we can generate. Here's one, the logarithmic spiral. In this case, theta is some more complicated function of r, and it's just a logarithm. Okay? And as you get away from the center, you know, the spacing between the arms is no longer constant. It tends to increase. So it's very simple to show that the distance in an Archimedean spiral between spiral arms is just a fixed number. It's just 2 pi upon a. Okay? The idea being you fix an angle, you go all the way around 2 pi, and you ask how much did the radius increase by, and you take the difference between the two values, and you get 2 pi upon a. So here's a little question, and I don't want the answer. Okay? Just think about it for a bit. What is the answer for a logarithmic spiral? What is the spacing between these spiral arms? Okay? You should be able to work it out. Are there any cash prizes for these questions, organisers? Maybe a chocolate egg later on. OK, so we know about spirals. I'll also need to tell you about the shapes that we rotate around these spirals, the generating curves. OK? When I made my torus, it was a circle. When I made my whelk shape, it was a semicircle. So I just want to rewrite the equations for a circle back in planar polar coordinates. Okay? So a circle of radius capital R, this is fixed now, may be described in terms of a single parameter theta. This is the angle around the circle, as x is r cos theta and y is r sine theta. Okay? So here's a picture of a circle. And as long as I tell you that you're on the circle, okay, you only need to know one number to work out where you are. Okay? Because if I'm here, you know, if I say start here and move an angle theta, then you get to here. You only need to know one number. Okay? I don't need two numbers to tell me where I am if I already know I'm on the circle. So I parameterize where I am on the circle in terms of one variable theta. Okay? And if theta goes not from 0 to 2 pi, goes from 0 to pi, then I would generate only half the circle, so it would be a semicircle. Okay? So here's another little question, and you have to answer this one because I won't move on otherwise. X is r cos theta, and if y is r sine theta, that will be a circle. All I've done is stick an extra factor of 2 in here. So what shape is this? Anybody? It's an ellipse. Fantastic. There, my little cartoon of an ellipse. It's an ellipse. I knew you'd be clever and get this one, so I made a more complicated one. How about this one? Okay? Instead of sines and cosines, I've got the same radius, So r sine theta here, and it's r times sine of 2 theta. So this guy's got double the angle as its argument. So what does this figure look like? Hush. Okay, well, it's much harder to... A twisted ellipse. Is that what you meant? So anybody that has to do physics courses, you might see these sorts of patterns on the oscilloscopes when you're mucking about with signals. Or if you're one of the parents and you remember your 80s discos, these are the sort of images that used to flap up on the wall and rotate around. So this is a Lissajous curve, okay? So you can make all sorts of fun curves with these parametric representations that just uses one variable theta. Okay, shells don't live in the plane. They live in 3 dimensions, okay? So we need to do a little bit of 3-dimensional geometry now. And it's not so much of a step up from 2D to 3D, okay? So there's a 3D Cartesian coordinate system where we talk about x and y and another component z. So if I want to tell you where I am in 3D, I need to tell you 3 numbers, the triple x, y, and z, okay? Somebody told me the length of a line in 2D in terms of Pythagoras' theorem and corrected me. Now, if I ask you what's the length of this line along here in terms of x, y, and z, can anybody tell me? Shout it out.
Square root of x squared plus y squared plus z squared.
And your friend will say, then square root it. Oh, you said that. OK, that's it. You know, it's dead easy. If you know a lot of planar geometry, it's easy to go up into higher dimensions. OK, so we know this length here. What about these helicospirals that I need to generate shell shapes? Well, what we can imagine is we're very good now at generating spirals in the plane. Okay, as I spiral around in the plane, if I just pull an x-coordinate downwards, that will create a 3-dimensional helicospiral. Okay, so that's what I'm going to do. I'm going to imagine there's a planar coordinate system, and I'll tell you where you're on the plane with x and y, but I'll have another coordinate z that pulls you out of that plane down. And if I start to generate spirals here and stretch them down, I'll get these nice helicospirals. Okay? And I can write, I can tell you where I am in the spiral by just telling you the angle I'm making. Theta is still a good parameterization of where you are on this curve. If I tell you you're on the curve, you don't need 3 numbers to work out where you are, you need 1. That's theta. So I'm going to write this r here, this spiral in this plane, is some function of the angle theta. Okay? And the z value, I'm going to imagine that z gets bigger as the angle increases. So again, it's going to be some function of theta. So f of r just means fr just means some function, fz is just some function. Okay? So this is a way of writing these spirals here. For a 3D Archimedean spiral, I just take r to be a theta. That's the old spiral I had in the plane. And in the z direction, as the angle increases, then the z value gets bigger. I get pulled down. Okay? So both r and z increase linearly with the angle. Okay? So this is my definition of a 3-dimensional Archimedean spiral. But as long as you tell me theta, I can tell you where I am on the spiral. So